Good afternoon, everybody. Thank you for joining us in our sustainability series, speaker series. We are very pleased to have this afternoon with us Professor John Kuhn from our own institution, the University of South Florida, where he is a professor and associate chair in the Department of Chemical, Biological, and Materials Engineering. Dr. Kuhn got his bachelor's degree from the University of Dayton in chemical engineering. And in the same area also, he got his PhD from Ohio State University. And then he did a postdoc at the University of California, Berkeley. He has focused his research recently on waste to energy processes, and has advised and co-advised 25 grad students to degree completion, and he has over 100 peer-reviewed journals. So a very productive career. In addition, Dr. Kuhn has won several awards in recognition of his work, including Excellence in Innovation Award in 2013 and 18 from USF, and also from USF the Outstanding Research Achievement Award in 2019. He has funded his research with awards from many agencies, including the Department of Energy, NSF, NASA, and others. He has created 2 spin-offs, and one of them is currently piloting biogas to diesel technology. So he's moving actually into that stage of proving the technology at pilot scale. And with that, I would like to welcome Dr. Kuhn. And to our audience, if you feel comfortable, please turn on your camera. Again, if you are comfortable with that. John, please go ahead.
Thank you for the invitation and the kind introduction. So sorry, my camera's not working right now. I got too many problems. I'm having a lot of technical problems this week. So I just came back from a regional meeting and my phone basically died. When I'm on that, so I had to order a new cell phone when I was driving back from the meeting. So it was a catalysis meeting. I won't focus too much on the catalysis part today, but to go through some of the recent research we've been doing over the last 5-10 years in this renewable space. As mentioned, some of the stuff I'm going to talk about is related to the USF spinoff T2C. So I just want to note that conflict of interest here at the beginning, and I'll describe some of the recent scale-up work towards the end of the talk. This is a semi-recent picture, pre-pandemic picture of my group. So about 10 PhD students and some master students at a given time, and work in kind of a few different areas, kind of CO2 capture and conversion a little bit. A lot of the group's been on biogas or biomass conversion, which I'll talk about today primarily, and a little bit on purification and photo and electrocatalysis. I'll go through a little bit. So there's some related pictures. And so one of the big challenges faced society right now is what to do with all the carbon. It's a little bit contradicting at times, but this report came out from the industrial DOE roadmap earlier, about 4 months ago now, and it shows the kind of how U.S. could go about reducing emissions to go to approaching neutral. So probably the important part, based off of static point in time, but the kind of current practice, the main thing is just being more efficient and electrifying things, which is kind of this green bar over here, with low carbon technologies, using electrifying with solar and wind, so renewable sources primarily, maybe nuclear as well, non-carbon based. It only goes so far, so there's kind of a big part where carbon capture and utilization and storage, the CCUS, is going to be used. So those are kind of the ongoing things right now to be able to lower overall carbon intensity and kind of all of our current infrastructure type needs. So it's a very demand topic, important topic right now in society. So kind of highlighted there. And one way we could go about doing it, some things with negative emission technologies might fit in that. So, George and I had a project where we're kind of looking at some of those things, the biomass to biomaterials that could be used carbon-based sorbents from biomass, or ways you might be able to make materials used for other things out of carbon that would be in the atmosphere, such that you're reducing the overall carbon emissions in a negative sense. So that's some interesting things that can go about doing that. This just shows kind of the breakdown of industry of where emissions come from. So it's kind of chemicals, refining, and a lot of the manufacturing, kind of top several there. So all industrial type things. That's usually large scale facilities where you can have kind of a big impact with if you can hit technologies in that. But then there's also a number of other things down the chain here where you can have impact in overall CO2 emissions. They're not necessarily what we think about is either industrial or transportation, but a lot with commercial and residential parts. So there's a lot of work that can be done with these areas. One thing that comes up a lot is hydrogen economy. So that's another report that came out recently. So do updates these quite frequently, but kind of the main idea is grid-based electricity with these renewables over here, or fossils with carbon capture. Making hydrogen and having that hydrogen replace hydrogen that would be used from non-natural sources, such as natural gas typically is where it comes from. So that'd be going to making ammonia or fertilizer or fuel upgrading, or just replacing this with the carbon being in CO2 for the carbon backbone of like transportation or synthetic fuels. So kind of an exciting time at some level in these things, but there's still a lot of challenges for us to solve. And so my background is in catalysis, so I did put a few slides in here, just since I think some or much of the audience is not going through these things frequently, but a lot of products we use, or most products we use, have a chemical used in some stage of their manufacturing. So if you think of any polymer or any fuel that we use, they all have catalysts used at some stage in production. So typically these are going to be heterogeneous, so solid catalysts for large manufacturing projects. So some pictures down here. Large scale products is what I mean. So these are some cobalt and other nickel-based catalysts we've made in the lab, are commonly used for this thing. They'd be kind of more intrinsic catalysts for fine chemicals, such as like pharmaceuticals and things like that. And a lot of the gross domestic product and chemical sales, and there's all very, very large markets for how these can impact a lot of society. So you can improve the catalyst that usually lowers the energy efficiency of either the conditions or the separations, or how much yield you can get per product or per feedstock you're making. And so there's a lot of impact that catalysts can make. What catalysts do is they change the activation barriers between products from different reactions. So here's just kind of a textbook case. You have a reactant. These delta G's are the activation energy. So if those are lower, they're more likely to go to one product or the other. And so one or two here. And this is just showing, for example, where you have one of them being 18. If you just can change this like 1 or 2 relative to each other, you can shift the selectivity, mostly from one product to another product. And that's how these things make useful downstream, because it simplifies the separation and things like that. And they go through a cycle. So this is just kind of a generic case from some publication I had earlier, but you have the surface has an empty site, it absorbs something, it goes to a different product and a different product. And then each one of these makes a circle here to go back to the empty site. So it gets used, every time in the one cycle, but it gets regenerated. And then you get whatever product, in chemical engineering, we just call them letters typically. So A, B, C, D, whichever one you would want. It's had a large impact. Several Nobel Prizes have won it, over the years. The most recent one is, Gerhard Ertl, about 15 years ago now, from Germany. And one of the things that he was winning it for was kind of understanding the fundamental chemistry or catalytic chemistry of ammonia synthesis. And after he won that award, he wrote this paper that's kind of referenced at the bottom in here. And he was making the case that the population increase during the last 100 and so years was all related to ammonia production from that Haber-Bosch cycle, to be able to make be able to grow crops more efficiently and per land area, such that we could support population base. Another common use of catalysis that every day is in our catalytic converter. So anybody that's using a gasoline engine, these have been around for 50 years or now, and they've really massively reduced the amount of emissions per year. So this picture here is from the LA area, but it shows the amount of bad things coming out of the car, how much they've decreased from 1975 to 2008. All these things you don't want to come out of the tailpipe of the car, but when they introduced catalytic converters in that time frame, over that time frame. And so kind of sit here and look kind of like big picture of a lot of these things for chemical engineering. At least we're trying to take things that are cheap and abundant feedstocks and make products out of them. and we're focusing on this reaction step primarily. My main part I'll talk about is the catalyst for those reactions today. And so usually I mentioned these are solid materials, so there's a lot of chemical steps taking place, all at very small scales. And this shows just kind of a depiction of how these reactant molecules can, diffuse into these small pores, and then they hit some often metal sites, react, and then diffuse back out. And so we're often, studying some set of these relevant time frame steps, in our lab, usually on the small scale. And then when we find successful things, kind of scale up to the next level, which I'll talk about a little bit later. And feel free if you guys put, type questions in the chat or ask, go ahead as I go through this. One area I mentioned was, direct CO2 conversion. So that's been an area we've been looking at in the lab with the idea that the hydrogen would come from electrolysis from renewable fuel sources. So we've been working on these kind of complex perovskite type oxides for this, where we can, they can convert CO2 to CO, which you could use a feedstock for different reactions to make any hydrocarbon product out of it. And it then basically stores the energy in some hydrocarbons that you would be getting from intermittent sources that would be making, like solar or wind, that would be making hydrogen from water. So you can kind of get this cycle here where you'd have a closed carbon loop. And this is kind of one of the big challenges if we go towards reducing carbon emissions directly into products and things like that. And our technology is kind of showed in the green here, so it kind of balances conditions, how much energy input and through the thermal needs you need to balance versus what kind of rate of product you get. So that's kind of one active area that Venkat Bethanamotha in my department also, and I've been active over the last 5-10 years. And I mentioned photoelectrocatalysis, another area I've kind of dabbled in. So this is interesting in the sense that instead of using thermal energy very often for the photo part, at least you're using light energy. So you can use direct sunlight as the light source or energy source, such that you can bypass all the heat-based things where you have a lot of intrinsic heat losses in that sense. So this is more futuristic probably, but things that would be ideal as we go through low temperature processes that can be operated intermittently off renewable energy sources or renewable electricity sources. So that's kind of another direction where the field will probably be moving much more in the next 10 years or so. And that kind of gives us a little background about what I've been up to, and kind of this, I'm going to spend the next half hour or so just talking about biogas and what we've done on that area. So biogas is kind of shown here. It's about half methane and half CO2 on a molar volume basis. So the good part is methane is kind of a nice chemical to work with, because it's, in terms of all the other things you might work with biomass, it's relatively simple compared to all these complex crops you might work with. The downside is gases are usually kind of much lower concentration than solids or liquids, so you're usually working at smaller scales. And in doing that, you're basically working at half the energy content of what a lot of people try to do with natural gas, because it's only half methane instead of mostly methane. So you have distributed part of the biogas with only half the energy content. So there's some challenges to try to do, chemical conversion of this to various products, as opposed to if you were using, fossil fuels. The upside is that we are trying to make diesel out of it, and very often this is made at places that use diesel, so there's a chance for a circular economy for these things. Another upside is very often since it's distributed, very often these are smaller scale, so often they're being flared just to prevent the methane from being emitted in the atmosphere. So there's kind of some sense of low-hanging fruit to make some chemicals out of this. Basically, energy is being wasted anyways. And in the last 5 or 10 years, electricity has been one product people have been looking at. So the nice thing about electricity is it's widely used, and so it's used everywhere. So that part's good. But the downside is you don't get as much value per product when you sell it as compared to chemical products. So I have some other prices over here, and this, I guess, is about 2 years old here. And I think, if anything, all these prices have basically went up 50% probably in the last 2 years since I updated this slide. So you can see diesel is often like $5 a gallon now, and all these other things have probably went up appropriately. So there's some nice products you can make, and the economy of scale may be overcome by the high selling prices of the product if you can make it efficiently. Very often there's some challenge with this. So one reason why we have a lot of biogas in the United States is food waste. So this term down here, if you're not familiar with, is organic fraction of municipal solid waste. So the U.S. is about 300 billion tons of waste, depending on which source you look up, EPA, or this is, Environmental Research and Education Fund. They're different by a certain amount, but about 25% of that is food waste and other yard waste and things like that are organic compounds, and they decompose basically when you bury them in the landfill, when it becomes anaerobic when you put the ground cover on them. And so this is where all this comes from. All this biogas comes from. So a large opportunity from the energy standpoint that could come about from this. There's also safety, since you have methane coming out of the ground at these places. That's could be fires. Might see kind of unrelated to that. Landfill fires are fairly common. So there's not the safest thing. And then the other part is the environmental aspect. So landfills are one of the not the top, but one of the top sources of methane emissions in the United States. And so another challenge to look at is what the contaminants are in landfill gas or biogas. So there's some listed here. So primarily for what I'm going to talk about, hydrogen sulfide is one that's concern. And so I mentioned the circular economy. This just kind of shows that in a little bit more detail from what we present sometimes for the startup company. Is that very often you're hauling the waste, then it goes hauling just goes kind of around the circle. And so you can have the source where you're collecting all that part, all the waste is where you might be making the fuel and also restocking the truck. So there's potential there for a kind of a nice close-knit market. And then kind of this just shows a lot of these are small scale, so in the order of 4,000 SCFM or lower. Other places you get biogas would be typically ag waste facilities, which also be very diesel heavy, and wastewater treatment plants, which again would be a place where diesel fuel could be distributed from. And kind of put this in context for this, plastics and microplastics and waste has been in the news quite a bit lately. And I'm only going to cover a lot of bullets here, but only want to cover a few things. If you want to kind of be more into how much plastics have been generated and wasted, this paper came out about a handful of years ago now, but it went through and described how much plastic's been produced and how much was going to be produced. And you can kind of see these numbers here. They seem gigantic, but I'll kind of put this in comparison to diesel fuel in a minute. And the sad part of all these things is only 9% of all these plastics have been recycled, and the most have been landfilled. And very little of it's biodegradable plastics. And the reason kind of put this in context, because sometimes it's hard to compare, these scales. We're talking about 83 million tons versus, 100 million barrels of crude oil per day. And so that's, roughly how much is used in the world, 25% in the United States. This ends up being about 45 million metric tons per year of liquid fuels being used from crude oil. So, I mean, that's per year up here. This is like the history of plastics, and they're about the same value. So just, how much fuel has been used ever, and all that's been burned, and the CO2 end up in the atmosphere is just kind of a gigantic amount. And again, very little of it has been renewable fuels to date at this point in time. And I put the big topic right now is the SAF, sustainable aviation fuels, and that's one step harder up than diesel from that part, just to the complexities of the fuel. And so what we're doing is taking that captured biogas and doing kind of a two-step process to upgrade it to diesel fuel. And we have some, heat and energy recovery. So what I'm going to go through is kind of the cleanup step here, these two reactor steps, and kind of the final product. I'll go through a few details of those in the next, few slides. And so this is kind of the broader picture. We usually kind of set this up in two different scenarios. As a block flow diagram of AD, so anaerobic digestion. So sometimes when we work with landfills, they already have the gas there, so we can go straight to the step where, the gas is being collected and cleaned up, as opposed to if we're working somewhere where we have to run an anaerobic digester, then there's the additional step. I'll come back to that a little bit in the economic stage, because that becomes important, as well as some of the contaminants are different, which I'll touch on a few different places. And so we clean up that biogas. Again, sulfur is kind of the primary culprit we want to get rid of. Then we run these through these two sequential reactors. So one unique thing about what we're doing is we're not doing any separations or anything other than just knocking out some water between these steps. So we're pretty much running things straight through from one step to the other. So that is one of the reasons you can do a little bit smaller footprint that helps the economics at small scale. and we're looking at some energy recycle up here where some of the steps require energy input, and we're using some of the undesired products that still have energy content to provide that. So there's some of the kind of integration of the whole system. We do it basically a kind of 4-step process to clean up the biogas. So sulfur is the first one. So this uses an iron-based material typically that works off like a hydroxide mechanism. So usually put the biogas through that bed first. You can remove the sulfur, and then you knock out any water after that. And then put it through a compressor if you want to make a slightly compressed part. For landfills and especially wastewater treatment plants, siloxanes are kind of emerging contaminant compound for those. So we're going to remove those. So the next step, then we kind of a polishing step that removes most of the other contaminants, except for the halides. Then we do something as a sacrificial bed kind of at the end to kind of clean up anything else that's coming there. But we kind of run through this 4-bed process of the raw materials, raw biogas before we send it to the subsequent steps. There's some cost associated with that, so we wrote a review paper a few years ago on that topic. Oh, that's actually that paper over there. To kind of go through what these costs are. Since the contaminant ranges can vary quite heavily from one source to the other, the cost can then range quite heavily for how much gas you're processing as well. There's a lot of contaminants could be in there for landfill gas. This is not particularly to show you any one contaminant, but just kind of block things down. There are various siloxanes that could be there. So there's kind of a group of these materials. I'll talk about those a little bit more later since we've had some other research on those. There's some sulfur materials. There's some halides. There's some other organics, non-methane organic compounds, and then there's some sulfur compounds that would be in landfill gas potentially too. So all of these vary from source of biogas from one to the other or landfill, because basically it depends on what type of garbage they take in and how to process and things like that, but mainly what type they take in to do that. So you get kind of a range of compounds and concentration of compounds. So typically we use adsorption to clean up, and this graph is from a kind of a shell sales pitch, but just kind of shows why adsorption is typically used. So this is the context of hydrogen sulfides. This shows the hydrogen sulfide amount that would be in like a natural gas stream for what they're selling, these different products, these code names over here. And this shows the gas flow rate. And so you can kind of think, if you multiply the flow rate times the concentration, you get how much is there. So tons per day of these things. So you can see 50 tons per day if you're at high flow rate and concentration, down to 50 kilograms if you're in that compound. This just shows what's typical for landfills. So like terms of what a maximum flow rate is and a maximum concentration of hydrogen sulfide. And this kind of shows more what the averages are. And so you end up being blocked down here since we're small scale in this bottom range, how you do it. So this for non-generable gas and liquid. So basically adsorption type processes are used. So do the small scale, those are the typical type things. On the right, it shows just some of those values of what they are. So comparing landfill gas to wastewater treatment plants. So typically, my experience with landfill gas, you get some number on this order of 50 approximately ppm here, and then it'd be higher for other waste sources, and then siloxanes again kind of a lower end for landfill gas than it might be for wastewater treatment, which is kind of dirtier type gas that comes out of the anaerobic digester from that standpoint. And siloxanes, the ones usually that people have heard less about. So these are materials that have not been around for more than 20, 25 years. They're nice in the sense that they work well in a lot of consumer products. The compounds are shown here on the right, but there's basically, they look like kind of like ringed hydrocarbons, except for they have silicon in the ring, silicon in the compound instead of all carbon-based materials. And these are often used as kind of, I'll say, polymer additives in some sense, but also in products that kind of have like a shine work to them, for lack of a better word. So if you look at kind of shampoo, for example, there's probably like a 33% chance you'd have some siloxane compound in them, and that's why they show up in land or wastewater treatment facilities quite heavily. They're in kind of shiny cell phone cases, things like that, quite frequently. So the problem is when they decompose, they become gas phase. Some of the compounds become gas phase, and that's why they come out with the biogas when they do that. And so they're more commonly used, and they're people were not really paying attention to these more than like 10 years ago for regulations. So there's just been increase of awareness of these for waste treatment over the last 10 years. In particular, I don't think I put a slide in here related to it, but manufacturer warranties, like if you're trying to make electricity, you'll have maximum concentrations you're allowed. In many cases, that's in this, I think it's in that review paper for at least what was in existence a handful of years ago. And so we looked at some accelerated tests. So since these concentrations are fairly low of what this might happen to a catalyst, we can't really run really long tests. So you can kind of see that here with the abbreviations. We added siloxanes and whatever concentration will be there normal over the course of weeks and months. And we added it all at once and kind of looked at the material property changes of the conversion, which I'll show on the next slide. So you can see, since these are silica based, when you add a lot of silica to the darker catalyst, that you can just visually see it's there because of the lighter color. And there's kind of a lot of information here, but the conclusion is if we're comparing these fresh materials in both cases for a couple sets of catalyst, and the lower number is the better. So you can see as we add more siloxanes, all these numbers increase down the chart. And if we kind of do some calculations based off of how much siloxanes may be there and how much can be added to the catalyst before it completely kills it, it basically means we need to remove all 90, like almost all the siloxanes, basically, that they're not to have a substantial effect. And so that becomes a kind of key contaminant for a lot of these processes to upgrade. You have to remove the siloxanes. It's kind of a take-home message from some of the studies we did for that. We also did some life cycle and economic studies for that, which just kind of comparing siloxane removal from landfill gas. This is just making electricity out of it, but just kind of how often you would need to remove those. And probably the main part is this is a siloxane removal unit. So basically you put some there that are large enough for 6 months and you have some downtime to replace them, or you put two in parallel and they can operate continuously, or you just don't put anything there and you just do maintenance on the equipment every time it breaks because the siloxane buildup. That was kind of the study we had done for one state agency. And so, of course, it depends a little bit on what scale you're at. So this is maybe similar to what I showed before. So some sort of flow rate and concentration. So if you're in the bottom corner here, that means there's not many siloxanes because your flow rate's low or the concentration is low, and kind of on this side, the opposite of that where it's high. So these graphs are just kind of the two different removal techniques we use to kind of show the cutoff between where it would be better just to do maintenance because there's not that much siloxanes versus it's better to add the removal units because you have a lot of siloxanes. You can kind of see there's a kind of a curve here that kind of breaks through that. So for some of the values before, so landfills would typically be kind of in this range here. So you're kind of in the borderline of where you would be depending on what these siloxane concentrations are. Probably a little bit higher than what exists in a lot of now, but I mentioned before, these are kind of increasingly more used products. So these probably shift more to the right as time progresses in the future. And we did some life cycle analysis as well. So we didn't see too much difference between what type of removal unit we used, but in all cases, they were much better than just flaring. So probably the right graph shows that more easily that we have a lot more potential for because of basically the sales of electricity, or the use of electricity, to not have an impact on the global warming potential. But I kind of go back to what our product of diesel fuel is, or project with diesel fuel. I'm going to walk through a couple steps. So some things that are different about what we do compared to what you might do if you were just trying to take a product that worked on a process that works on natural gas and scale it down. Is we're not removing any of the CO2. We actually use the CO2 as a reactant, or some of it as a reactant to help balance out the reaction. I'll talk about that part later. We're tuning what goes into this first reactor with basically how much steam we added for the hydrogen, such that we can directly send that ratio into the second reactor. We don't need any water gas shift reactor to adjust this ratio here, or some sort of hydrocracker to adjust ratios here before the separation. We're not doing a lot of distillation here, and we're adding oxygen in as well, which I'll talk about, but we're not separating out the nitrogen. The air separation is usually a very energy intense process that kind of overwhelms things. And the nice part of what we're going to show is the fuel here is it's drop-in. So drop-in means it can be used directly as diesel fuel in a diesel engine, and it meets those criteria. And we're in the process of having that at a larger scale with engine testing as well right now. But the good thing about the sulfur poisoning the catalyst is we have to remove it, and then this becomes a very low sulfur fuel on the way out. It's also very low aromatic, so it's very kind of clean fuel for that. And the catalysts we use in these two steps are kind of the key of how we can get this to work, which I'll talk about in the next couple slides. This shows some pictures from my lab, so it's kind of typical in the catalysis area. You're operating on what's called a microreactor, so there's not too important the details here, except for 100 milligrams is small, 100 standard cubic centimeters. These are all kind of small things where you do like initial tests. So this might be like if you were putting like some catalyst like this in a refinery, it might be like 1 millionth or 1/10 millionth of what a commercial size unit would be. And we can scale up to a certain amount in the lab. So that's kind of, if you see some things from the left to the right here. This is 1/8 of an inch. This is 1 inch tube. So it may still sound kind of small, but it's basically about a 30 to 50 up scale up. And one of the reasons we can solve a lot of challenges here is we can start operating at pressure, and we can start using powder instead of pellet catalyst. That solves a lot of the steps that would be problems like at later down. When you go to really large systems, typically you have to still use about 1 or 2 inch pipes because you need the external surface area to be high for heat transfer. And so another way to say that is you don't want one large tube. You want maybe instead of one large tube, you're gonna have like 100 smaller tubes that are all kind of packed in some sort of array inside one system just to have the external surface area for heat transfer. So you solve a lot of problems just going up from this scale, which we could do in the lab. But we also went to a local landfill and got some gas compressed with this is a natural gas compressor we bought, so we could take real landfill gas and then use it to clean up and then test it in the lab. So we were able to solve some of those earlier stage, or solve them and work with them at the lab scale still before we went to the next scale. Kind of a little bit about the reactor part is the first reactor is called tri-reforming. So historically, methane reforming is the one where that name, the reforming part, comes from. So that's with steam. So this is often used where methane's from natural gas. You add steam in or water in, you make CO and hydrogen. So the hydrogen is often used if you were trying to hydrotreat petroleum products or make ammonia. This would be a typical process for that where you're trying to make hydrogen. We're not looking just at the hydrogen directly. We want to have something where the hydrogen to CO is a 2-to-1 ratio, because most polymers or most hydrocarbons you want to have a 2-to-1 ratio. So we balance that out by reacting some of the CO2. So you can see that if we react 1 CO2 with methane, then we get a 2-to-2 ratio. And then you can balance these out by reacting 2. If you just want to do those 2 steps, 2 steams and 1 CO2, then you would get, you could get this worked out to be a 2-to-1 hydrogen to CO ratio just with balancing between CO2 and steam. And the nice thing about that is then you're reacting some of this carbon that would be otherwise emitted back to the atmosphere if you're just trying to use it, the methane component only. Now, both these reactions require heat input. So these both are positive values, so they're endothermic. The one way we get around having 2 largely endothermic is adding a little bit of air in, and the oxygen air does this partial oxidation step. So it is slightly exothermic, but the nice thing is it's not it's kind of more neutral in terms of energy you need, but by having it be neutral, it's better than having the enthalpy needed for the heat input of those reactions. So we can kind of balance this out. So you can see these numbers, we average around 220 by reacting some like 40% of the oxygen. By these mechanisms, we can get the heat of reaction down to more like 135 at at typical reaction conditions. So we need less energy input at that step. Is kind of the advantage of that. Here's some of the various catalysts we've used over the years. Probably is not too much I want to mention necessarily on this, but we spent some time to go from powders to pellets because we needed those to scale up. We do some fundamental studies and things like that, and we'll get into just to understand why they're working and things like that. But we're able to tune these properties in where we could get high methane conversion, really high CO2 conversion, in this 2-to-1 ratio range over the whatever temperature input we would have at this fixed input conditions up here. So that worked well. These are just kind of shows the progression of some of the catalyst materials here, and we started with the powders on the small scale, and then we went up to kind of upgrading conditions and making this more realistic, increasing pressure, space velocity, adding real landfill gas. As we go up in here, we're able to maintain kind of this performance range we were interested in of the kind of high. The most important thing is getting the high methane conversion, and the most important 2 things: CO2 ratio around 2, then the higher we can get the CO2 conversion without knocking those out of balance is the next most important thing. And so that gives us basically this input to the second reactor here, which we worked with this. So I worked with Dr. Joseph, who's also in our department for this. He worked on this reaction for quite a long time. And this is an interesting one because you're trying to not necessarily make a very active the best active catalyst, but make one that makes a certain product cut. So he worked with these eggshell type catalysts. And so you can see if you would take some of these apart here and cut them in half, they would look like this. Is why they're eggshell, because the cobalt is only on the outer 20% approximately of the shell. And that distance or how thick that is, allows you to make certain length of hydrocarbons. And typically we're trying to look at things that are C5 plus, because anything that's C5 plus is condensable, and that's at least gasoline at that point in time, as opposed to gas phase products. And so in the second step, we're able to convert CO and get these range of products, not making too much CO2 in that stage, a lot of things that are liquids. And then this basically ends up being about 40% of the energy content recycled to the fuel. We can push this higher, but since that one step I just mentioned before, this still needs energy input, we're okay with having some of these lighter products we can burn, provide the energy content for that step. And so these are all larger lab scale studies that was in this paper. If people want more detail, we based a lot of the aspect from. So here are some details of what the fuel looks like. So if you're not in this, there's it's called a piano analysis typically. So paraffins, isomers, olefins, naphthalines, and aromatics, so kind of cyclics instead of that. And so I mentioned we don't have much. It's our fuel's more clear, or the product's more clear. That's because there's not many aromatics, which you can see kind of basically comparing these tables down here. So the nice thing about that, if you've ever seen like a semi truck start up at a red light, they have a lot of aromatics. Those don't burn very well when you're kind of getting started. That's why all the particulates come out at the top. And so that happens. It's much cleaner at that stage, for the fuel that has much more, N-alkanes, which is kind of this component here. And so this is, nice. We can clean this up so that this matches pretty well to commercial diesel, which is in the red. It's slightly shifted to lower because we have less aromatics, but it still meets the criteria. And we can distill it a little bit if we want to purify it to make it a little bit higher. Sometimes we don't worry too much about this because a lot of times people are going to blend it with fossil fuels in the near future anyways. So it'll decrease everything by, be more compatible with all the existing infrastructure, but also not have the properties on all its own. So we do a lot of these ASTM tests, which are kind of highlighted here. We can meet them. In many cases, we exceed what they are. So this is here if people want to ask questions about it. But the fuels, everything we have is it's good to be used in a unit. I probably skip that slide. I do get some questions about economics at times. So the economics are a little bit tricky to answer because there's a lot of credits, and the credits change fairly. They're market based, so change frequently. But kind of the main idea is if there's no credits, is a renewable identification number. These would be credits you would get for sale of the fuel. You need about 1,000 SCFM so to be profitable. So this would be a little bit lower than average by mean landfill or median. Average by median would be able to do that part. And this is selling at a certain fuel price. I think it's about $3 a gallon. This number is probably when this paper came out. But if you were applying these RIN things, credits to the fuel, you might get $4.50 a gallon on top of the sale price of the actual fuel for that. And then these can change, pretty rapidly. So we always put a grain of salt with what those things are. But we can still be profitable without those, but those make it very, very advantageous. And those were all numbers based off of just having the landfill gas available. We can redo some of these other things if we start with biomass that would be being hauled to an anaerobic digester. So basically adding on the anaerobic digestion step on top of the other parts I talked about. And so we can compare some of the costs for that. And I can go through this, but anaerobic digesters, the rates are pretty low and they're pretty gigantic, so the capital cost becomes a pretty dominant part of everything. I kind of like looking at this because it kind of puts the whole waste processing to fuels in perspective. Is you always have to take into account what what we're paying or what we're being paid for to take kind of on the front end. And so, landfill is operating on a tipping fee. So, most things with biomass, you have to think you have to buy it and have it transported to you, or there's some cost with that, which would, show up under the feedstock cost of how much you're paying for a ton. And if this paper was in a journal that required us to use all SI units, if you're kind of wondering about why we have tons and liters, dollars per liter, break-even cost of diesel, and those numbers. But so the top cases that we were paying to take it, we did a case where it was neutral, and then we did some cases where we were being paid to take the waste, to process it. So you can see that's a gigantic impact on these. So if you want these in dollars per gallon of fuel, you just multiply those by 4 about. So if there was something here, you'd be in the 4 or 5 range, but it gets down pretty low if you're being paid to take the waste and then process it. So there's a kind of a wide range of things that could go about, or the different scenarios you have for this range of how the finances or how the business actually works, which is a kind of interesting in itself. Kind of in the last couple slides, we worked with somebody on the advisory board of our department. We were kind of getting started with this. You can see it's 10 years ago, and he sent us this picture and said, you guys need to prove it by getting something to this scale and taking it around places and show it works. And so we started working towards that, and we spun the company off. We took us a few years to get things kind of out of the lab. So this is a company that's in South Carolina that specializes. These are some of the master's students that work for the company that spun off. Start designing this, it took about 5 years to kind of get to scale. So this is 24 SCFM, so it might be 1/100th approximately of what a landfill might be if you were putting it there. And so we took it to a dairy farm first. So this is about a size of the digester is about the size of a football field, and you can see there's some flares there. It's about 20 feet deep below that, so it's pretty gigantic. And we siphoned off kind of a side stream of some of their fuel, and for our first test, a couple of years ago. And so you can see some of the fuel came. This is all dairy waste, by the way. Came out. Everything worked pretty well, but we worked a lot of kinks on the pilot system at that scale. We were lucky to get some DOE grants for this project after that, so we did this next round of tests at Citrus County. So this is their landfill there. We did 7 months of testing there. So one thing that comes up with catalyst is we can never really test 7 months in the lab. So we were able to test 7 months on stream here, and so that gave us some verification of the catalyst working at least that long. So that was a good successful test in that part. And then we worked with Pinellas County. Some people might be familiar with South Cross Bayou. We did some tests there on their ag waste 80 facility late in 2021, so about a little over a year ago now. They collected all this in this container here. We took a side stream off of it. You can kind of see it's back in the picture, not the rest picture, but did some tests there, and we're kind of at the stage where everything worked well at the pilot scale. So it's looking at moving it forward to the first commercial facility now. So I think I probably went about how long you want me to, so I can probably skip through that and leave here with some of the funding sources we had. So I'm happy to take any questions in voice or chat.
Great, John. Thank you so much. It's very nice to see that you are moving now past the pilot, and I assume you're raising money for building the first facility.
Yeah, we're looking at a couple of different scenarios in U.S. and elsewhere, so the economics are a little bit different, and by country, I guess is a good way to say it.
Yeah. We would welcome questions from the audience. Perhaps I can start by asking. You spoke about the catalysts, and those catalysts often they contain rare earths like nickel, for instance, which are also in demand these days and will increase their demand over the years for renewable energy systems like batteries and photovoltaics. Do you see any cost or supply chain issues as that demand is increasing?
We've certainly seen, since you mentioned nickel prices, it's kind of a catch a little bit. Nickel prices have certainly increased a lot over the last 2 years, but it's not as much as cobalt, which is the other primary metal we're using. So it has an impact, but maybe not as much as if it happened to cobalt, it would have been worse.
Sure. What about reusing? I mean, can you extend the life of those? Can you recycle, reuse them? Without becoming too technical, just kind of, we keep talking about, trying to improve sustainability by reusing and recycling materials.
So certainly we can regenerate them. I mean, from the company's standpoint, the company's not guaranteeing anything longer than 7 months because that's what we tested it at. So I mean, we are aware and thinking about how you would, take the catalyst back and then do studies about regenerating it and using it in the future.
Okay.
Material that's certainly on the radar. I know industry in general, if they use precious metals, they're very efficient about collecting and recycling because they've had to, but not necessarily with the metals we're using here.
Okay. If you have a question, you can either post the question or you can raise your hand or just go ahead and ask it.
Life would be easier if we could use iron catalyst for everything.
Yeah, plenty of that and a lot more affordable. Let's see if we have any questions from our audience here.
It says the chat's muted on my screen, so maybe.
No. Let me check. Lauren, are you following the chat? We cannot hear you, Lauren.
Sorry, I don't see any questions currently in the chat.
Okay. Then I'll ask another question I have, John. As you are making diesel, what percentage roughly of the cost of your diesel is related to the cleanup of the biogas that you described earlier in the presentation?
I had a number there, but it probably was in 2 different units.
Okay, maybe I missed it.
So it's because so this, so it ranges from this in this.
Okay.
Like order of magnitude, kind of in the scale here. So the problem is I probably didn't have any numbers of in normal meters cubes. That might be 70, might be a typical value, 70 per 70 per hour. So you can multiply that out, but it ends up being fairly minor.
Okay.
I think I had one slide. Actually, that probably was the wrong slide to pull up for that, but I think I skipped through very quickly. Yeah, so these are the capital costs or the materials costs, but we're talking about hundreds of $1,000s per year
for the catalysts.
Yeah, so like 163 and 19,000. Oh, these are for the adsorbents for the cleanup.
Okay. All right. Any questions? Anybody? Anybody from our students or faculty? Everybody's very quiet on Wednesday afternoon. John, as far as commercial development, so you envision co-locating your system at landfills or anaerobic digestion operations?
One place we're talking to has that capability. Basically, they have two things pretty close together, and they're able to combine to basically increase the size. Right? I think that's what you're getting at, right? Yeah. So co-locating of anything. I mean, this becomes in certain places, like I know California being one of them. They're much more diverting the waste and doing AD before they put it in the landfill, rather than using the AD as the landfill. And then it's kind of the same idea where you could co-locate two things because you're processing the waste and you have the older waste that's in the landfill kind of coming out the same. You combine them because they're coming out at the same time. The delay of biogas coming out, there's a delay on the order of like 5 years or so from when you put things in. It's a slow process.
And do you see more anaerobic digestion systems being developed in the US? I mean, Europe traditionally is very pro anaerobic digestion. The US, we've been lagging. Do you, as you go around or you look around, do you see more and more of those at large scale?
I'm not sure about, like, a lot more people are thinking about it, I guess is maybe a way to say it. In the US, that part.
Okay.
It's coming up more than.
Okay.
I think
there's
Bandy
one
has a
question
question.
coming in the board. On the
Yeah.
screen.
One of our colleagues, I think, Subrata, is typing a question.
Again, yeah, I had calls intermediate, so if I missed it, I'm sorry. My question is on the chat.
Sure,
Are you working with any Florida dairy owners here, and if so, which ones and which part of Florida?
The pilot test we did with Alliance Dairy. It's about 45 minutes west of Gainesville. They already have a large digester there, so it's about 1,500 SCFM. So about reasonable size compared to a landfill for that part. We were only doing the side stream off of it, but I think here for a second, it takes a pretty good amount of cattle to have a reasonable size of biogas from that. I think they had, if you Google the thing, they have some YouTube videos on there that kind of go through all their renewable energy operations there. I think it might have been 10,000 cattle to get 1,500 SCFM.
Okay.
So it's the largest one. It's the largest dairy farm in Florida, I think.
Wow.
That one is the largest, so that gives you an idea of that we really need big size operations, right?
Yeah, I believe California has a lot more larger dairies, if you will. And how about the cold weather areas, for example, the Midwest and all?
Yeah, we talked with people in Wisconsin and things like that.
Is the temperature a problem?
No, that's not an issue.
John, we cannot hear you.
Oh. Temperature is not the temperature of the operation. The temperature of the environment is not an issue.
Okay.
Maybe, Subrata, you're referring to the anaerobic digestion itself?
Yeah, exactly. If the digestion is not as efficient, I mean, is the biogas utilization?
Yeah, when they build them, they install heating systems when needed. They turn it on. They are trying to keep the temperature, depends on if it's mesophilic or thermophilic. Thermophilic will need a lot more energy, but they're faster. They produce a lot more biogas, yeah. Any other questions? John, one more I had. In one of your diagrams, you showed diesel coming out as the main product, and then light, I remember you call them light gases, right? Do you see, and you are trying to recycle those back, do you see any use for those if you were not to recycle them back into the process?
Yeah, I don't know which might have been this one, but typically we use these light gases we burn them and for this endothermic step here.
Okay, so you use them as a source of
heat back into that. Things that get discussed kind of for similar process in there is if you could, use renewable energy, electricity, basically you could do electric heating, right, instead of a gas burner. And then you could reuse these gases, either recycle them or make LPG out of it or other things like that. For our particular thing, we haven't looked at that too much, but that's because we're not doing the air separation. So there's a lot of nitrogen in that stream. So we're thinking there's going to be a costly. We haven't looked at the cleanup, but I think it's not going to be beneficial to clean that up.
Okay. Well, last call for questions. All right. If you have a question and you want to ask Dr. Kuhn later on, feel free to email him, look him up in the Chemical Engineering Department website. You can find his email address there. And with that, John, I would like to thank you for joining us this afternoon and sharing with us not just the research, but also how the research has advanced now to pilot scale and is moving into commercial development. That's really very, very exciting. That's what we want to see more and more in the renewable arena. So thank you so much. And thank you, everybody, for joining us. And we'll see you next time with our next speaker.
Before we end,
Yes.
John, I would like to thank you for inviting your students for this speaker series. I was at Bull Market today, and we ran into one of your students, and we were telling him about this speaker series, and he said you're his professor. He gave you some high reviews as a professor, and that you have invited him. So thank you very much.
Okay. Well, thanks for having me. Sorry for the technical difficulties. I look 5 years older than the picture I sent, I think.
No problem. Thank you, everybody.
Thank
Bye-bye.
you, Dr. Kuhn.
Bye.
Bye-bye.
Thank you, Dr. Filipides.
Thanks,
Thank you.
Lauren and Shirley and Lon.
Yes.
Bye-bye.
Thank you, everyone. Have a good one.